classes on fundamentals of electrical engineering. We were on DC machines, and this is the second section. And the second section, though we had revised basics as also some kind of speed control, now we are going into the heart of the DC machines again. Recapitulation, of course, and consolidation, wherein we are trying to look at torque relations. Okay. So the torque relations, I think quite a large number of things were discussed, and so it's easier to go into the first problem and then revise as also perhaps introduce something new if it is so, if it is required. Okay. A 240 volt first problem. A 240 volt DC shunt motor with an armature resistance of 0.5 ohms has a full load current of 40 amps. Okay, so I suppose this is clear. It's a shunt motor. 0.5 ohms happens to be the series resistance, armature resistance. So 40 into 0.5, 20. 240, if you deduct 20 from there, that's going to be the back EMF, okay, for this particular situation. Okay. Find the ratio of the stalling torque to the full load torque when a resistance of 1 ohm is connected in series with the armature. So now another resistance is also going to be introduced. So that's another 1 ohm. But at the same time, there are two different torques. One is stalling torque. The stalling torque is associated with a situation wherein you have locked the motor, you have blocked the rotor. So in other words, lots of current is flowing. Why? Because there is no back EMF, because the rotor is locked, the speed is 0, so there is back EMF is 0. So the entire applied voltage flows through the two resistive components. One is the armature resistance, and another happens to be the 1 ohm, additional 1 ohm that has been introduced. Okay? So this is the situation. Okay? So that gives us an understanding of the stalling torque. But at the same time, since speed is not there, you can't use the expression of 2 pi nt by 60 is equal to EB by A, because torque is because we see that EB is equal to 0 and speed is also equal to 0. Okay. So now just the power equations or the current will be sufficient for explaining the torque, because the torque for a shunt motor is proportional to the current. Okay. So what we have is stalling torque is given by it being proportional to both flux and ampere as usual, with n equal to 0, and so EB is also equal to 0. So armature current is given by the entire voltage, as was mentioned earlier, divided by the two ohmic values. One is the armature resistance, the other is the 1 ohm, additional 1 ohm. Okay, so 240 divided by 1.5 gives us 160 amps. So this is the stalling torque, and the other torque is, this is the stalling torque proportionality or current proportional to the stalling torque. The other is the full load torque, and the full load torque is proportional to 40 amps. So 160 divided by 40 gives you 4 as the ratio of the stalling torque to full load torque, wherein we have just used the torque expression, the understanding that torque is proportional to both flux and current. But in this case, in the shunt motor, the flux is remaining constant. I suppose the new introduction could be the stalling torque. Okay. So moving on to the next problem. 200 volt, 2000 RPM, 10 amps, separately excited. Okay, so separately excited means it's still a shunt motor, but at the same time, flux remains constant. Okay, as in a shunt motor, but at the same time, there is no, you can control it separately. Okay, has an armature resistance of 2 ohms. Okay, so 2 ohms, 10 amps, 20 volt, and 200 volt. If you deduct from it, 180 volt. Okay, so those things should come immediately as you read the problem. Rate and the speed, which is proportional to EB, which is equal to 2000 RPM. Rated DC voltage is applied to both the armature and the field winding of the motor. If the armature draws 5 ampere from the source, the torque developed by the motor. This is very simple, because we have an expression for torque as equal to 60 into which has been taken by manipulating what we spoke about earlier. So T is equal to 60 into EBIA divided by 2 pi. Okay, so 60 is the EB. Okay, so as was mentioned earlier, EB is easy. EB is 200 minus 10 into 2. Okay, but of course it is at 2000 RPM, and we want the torque when it draws a current of 5 ampere, which or in other words, there's another EB. Okay, so we see that 180 is proportional to 2000, and EB2 is the situation when current is equal to 5 ampere. Okay, so it drops only 5 into 2, 10 volt across the armature resistance. So 200 minus 10 is equal to 190. So the new speed can be easily computed based on the fact that 180 by 190 is equal to 2000 by n. Okay, so n is the same as equal to 2111. Okay, so once speed is there, you have 60, you have EB, that is EB2, you have IA, which is equal to 5 ampere. You have everything, including N is equal to 2111. Okay, so substitute everything, and you see that is the same as equal to 4.30 Newton meter. Okay, so torque is normally specified in Newton meter. Okay, so moving on to the next problem. Yeah, that is the fourth one. Separately excited. Okay, so as you read, you can compartmentalize, as I said, as I often say. It has an armature resistance R is equal to 0.05, very small. Field excitation is kept constant. At an armature voltage of 100 volt. Okay, so that's the voltage given. The motor produces a torque of 500 Newton meter. That's zero speed. Okay, so speed is zero, or in other words, it can be called as a stalling torque. Okay? Let's hope it's a stalling torque. Okay? Neglecting all mechanical losses, the no load speed of the motor for an armature voltage of 150 volt is what. Okay, so this is what is asked. Okay, so as was mentioned earlier, when you are having a stalling torque, you have a current. Okay, and how much is that? That is that's given by 100 divided by 0.05. And so what's the power developed? Multiplied by another 100. Okay, so this is the power developed. Okay, and so so in that sense, what could be the speed? What could have been the speed which has been blocked? Okay, that will be given by, as was mentioned earlier, you can find it out by the power divided by 500. Okay, so that gives us 400 radians per second by 500, because 500 was the Newton meter associated with this particular. So 400 radians per second used to be the, could have been the speed which has been blocked. Okay, so now on the other hand, instead of 100 volt, we are applying 150. So what's the no load speed? It's easy to just simply extend the idea to seeing that now the speed is going to be 600 radians per second. Okay, it's just another, again, a new idea, in the sense that the stalling torque, there is supposedly a speed which has been utilized and which is associated with 100 volt. So we now associate it with the new voltage, applied voltage, which is 150. Okay, and we use the situation that it's a no load situation. Okay, that's all. So yeah, so the next problem is the fifth one. A DC motor has the following specifications. Okay, so that's the nameplate things that is given here. 10 HP, 37.5 amps, 230 volt. Okay, and flux per pole is as equal to 0.01 Weber. Okay, so per pole is always what is specified, because each pole is responsible for creating the voltage, okay, in each of these conductors. Number of poles is equal to 4. Number of conductors is equal to 666. Number of parallel paths. So looks like it's a 4. Okay, so how many poles? Yeah, 4 poles. So it's a wave wound machine, okay, because the paths are only 2. Armature resistance equal to 0.267 ohms. The armature reaction is negligible and rotational losses are 600 watts. So many things are given. Okay, the motor operates on a 230 volt DC supply. If the motor runs at 1000 RPM, the output torque produced. Okay, so this is a torque session. So we are always going back to torque. Okay, so let's start from the very beginning. What we have? We have EB. Okay, because we have been given so many things. Phi is given, Z is given. So we start with EB. Okay, because all these things are given. So what is EB? EB is given as equal to phi Z N by 60 into P by A. Substitute for everything, you get it as equal to 222 volt. Okay, what is next? We need to find out the applied voltage 220, so we can find out IA is equal to 230 minus 222 divided by the armature resistance 0.267. This is a little different from the earlier problems. So we get the armature current as equal to 30 amps. Okay, and now we realize that the power output is given by EB into IA. Okay, so EB is 222, IA is 30, so we have 6060 watts as the power output. Okay, so torque is very easily computable as equal to 60 into, okay, so the earlier equation, so 60 into 60 into EBIA, which is 6060 divided by 2 pi n, which is equal to 1000. Okay, so substituting everything, you get it as a very nice value, 57.81 Newton meter. I suppose the small subtle differences that have happened are also being made clear for you, okay, or accessible for you. Okay. Yeah, so what we have, what's the difference here? The difference that you using phi Z N by 60 into P by A, you can compute EB. Then you can also compute IA on the basis of V minus EB by R. Okay, so because it's a motor. Okay, so now let's see what problem 6 has to offer. A separately excited DC motor runs at 1000 RPM at no load when its armature terminals are connected to 200 volt DC source and the rated voltage is applied to the field winding. Okay, so yeah, so much of data is given. Separately excited again 1000 RPM, and then the terminal voltage is 200 volt, and the rated voltage is applied. Okay, so rated voltage is applied to the field winding. Okay, the armature resistance of this motor is 1 ohm. The no load armature current is negligible. Okay, so which means that whatever is applied now becomes EB. Okay, because the no load the no load armature current is considered to be 0. Okay, is negligible. Okay, when with the motor developing its full load torque, the armature voltage is set so that so now armature control is happening such that the armature voltage is set so that the rotor speed is 500 rpm. Okay, so I suppose full load is being delivered and then the armature voltage is set such that the rotor has a speed of 500 rpm. Okay, so that's it's a two-way control. Okay, so when the load torque is reduced to 50% of the full load value under the same armature voltage conditions, okay, so armature voltage has not changed. Okay, the speed rises to 520 rpm. Okay, neglecting the rotational losses, the full load armature current in amperes. Okay, so many data has been given. We will codify them one after another. Okay, so let's see. It's a separately excited DC motor, so torque is proportional to both flux and current, but in this case the flux is constant, so torque is proportional to current. Okay, so in that sense we see that when the torque is reduced, okay, as is the case when the speed is brought down to 520 rpm, then we have a third case. Okay, in fact in this problem we have three cases. One is when we are having no load 1000 rpm and then 500 rpm and then 520 rpm. So at that time I3, okay, I call it as I3 as is the same as equal to 0.5 I2 because I2 refers to the full load condition. Okay, and so now we have EB1, EB2 and EB3. So EB1 is of course 200. Why? Because the armature current is considered negligible, so there is no drop, so applied voltage is fully converted into back EMF. So EB1 is equal to 200 and so EB2 by EB1 using the speed ratio, you can see that it's given by 500 by 1000. So EB2 is equal to 100 volt. Similarly, if you replace 500 by 520 rpm, then we see that we can also get EB3 as equal to 104 volt. Okay, so now we are having three voltages and so three currents need to be obtained. Okay, so how do you do that? Okay, so we realize that EB2 is the same as equal to 100. Okay, which is the same as equal to V, the applied voltage V minus I2 into 1. Okay, because the ohmic value of the armature resistance is 1. Okay, similarly EB3, which is equal to 104, is the same as equal to the same old applied voltage V minus I3. Okay, and we know the relationship between I2 and I3. So just for that we deduct EB2 from EB3, so we get 4 volts, which is the same as equal to V minus V is 0, and we see that I2 minus I3, and I2 minus I3 where I3 is the same as equal to 0.5 I2 as was mentioned earlier itself. Okay, so now we see that so I2 can be calculated as equal to that is 4 is equal to I2 minus 0.5 I2, or in other words it's 0.5 I2, so I2 is the same as equal to 8 times. Okay, it's a simple problem, but then it's a little different from whatever problems we have been doing in the earlier session on torque. Okay, so moving on to what is this problem? We are having a seventh problem. A 220 volt DC series motor. Immediately torque is proportional to, torque is where we are focusing, so torque is proportional to Ia square. Okay, drawing a current of 30 amps, so 30 square. Okay, from the supply. Armature and field circuit resistances are, so there are two resistances, one is the armature, the other is the field resistance, they are in series. So 0.4 and 0.1 is equal to 0.5. Okay. The load torque varies as the square of the speed. So torque is proportional to not just Ia square or phi into I, where phi and I, where phi is proportional to I, it's also proportional to speed square. Okay, so that's another new idea that is being helpful to us. The flux in the motor may be taken as being proportional to the armature current. Okay, as we guessed right a little time back. To reduce the speed of the motor by 50%. Okay, so now N is going to go down to N by 2. Okay, the resistance in ohms that should be added in series with the armature. So this is the problem. Okay, so the first statement or the first idea that should be in our mind should be that torque is proportional to phi Ia. Phi is proportional to I. On the other hand, if they give some 0.4 into I, etc., you can use that. So phi is proportional to Ia square. It's also proportional to N square. So in a roundabout manner, I is proportional to N. Okay, so we already have a speed being given, and so with the next current, when the speed is brought down to 50% of the value, current also comes down because current is proportional to speed. Okay, So we see that EB1 is the same as equal to, we have been given 30 amps and we already guessed that 220 minus 30 into 0.5, 0.4 plus 0.1 is 0.5, gives us 205 volt, and so N2 by N1, which is equal to 0.5, gives us IA2 also as 15 amps as was mentioned earlier, because IA1 is 30 amps. Okay, so all these things can be put together. EB2 by EB1 is equal to N2 by N1 into 15 by 30. Okay, because of the flux relationship. So we see that because it's series motor, don't forget that. Please don't forget that flux is proportional to armature current. Okay, that's the reason. And EB is proportional to both N and phi. Okay, so that's the reason why we are having EB2 by EB1 is equal to N2 by N1 is equal to 15 by multiplied by 15 into 30. So EB2 is equal to 205 by 4. Okay. So now EB2, you can say that 205 by 4 is the same as equal to 220 minus 15 into R, because the additional resistance is there. And so you can calculate the value of R as 11.25. Deduct from it 0.5 because they happen to be the armature resistance and the series resistance together. So we get an answer as equal to 10.75. There are other methods also which are just outlined a little below. But I suppose this is enough. This is the direct way of solving the problem, wherein we realize that the speed is proportional to current. So we have both the currents are obtained immediately. That is 30 amps goes down to 15 amps. Okay, speed also goes down. Now the only thing that has to be accounted is that there is an additional resistance. Okay, so EB1 and EB2 are accordingly related. Okay, that's all. So let's look at the 8th problem. 220 volt, 10 kilowatt, 900 RPM separately excited. Okay, so immediately something has aligned itself in our mind. Okay, has an armature resistance RA is equal to 0.02 ohms. When the motor operates at rated speed with rated terminal voltage, the electromagnetic torque developed by the motor is given as 70 Newton meter. Neglecting the rotational losses of the machine, the current drawn by the motor from the 220 volt supply. Okay, so now what all do we have? We know that EB into IA is equal to 2 pi NT. Okay, so we have 220 minus IA into, we don't know the current, and that's what we're supposed to calculate. So 220 minus IA into 0.02, that's given armature resistance is multiplied by IA is equal to 2 pi. Okay, and then N is given as equal to 900 RPM, T is given as equal to 70 divided by 60. Okay, so the only unknown happens to be IA, and it's a quadratic. Okay, of course you can solve for it. Okay, on the other hand, you can calculate the right hand side. So what does the right hand side tell you? It tells us, of course, you can set pi is equal to, for the time being, as 3. So 2, 3 is 6. So we have, you can compute 2 pi into 900 into 70 by 60. Okay, substitute, put pi is equal to 3. So you get the value, and then substitute for different values of IA. You will see that you can solve it, or you can, by substitution, you can see that B is better. Okay. In fact, I normally do with substitution. That's why I suggest this method, because this is what I'm trying to do, suggesting some easy methods. Okay. So last problem, the last slide is the 9th one. A shunt connected DC motor operates at its rated terminal voltage. Its no load speed is 200 radians per second. Okay, that's different from, so 2 pi N by 60 gives you N is in RPM, so 2 pi N by 60 gives you the radians, okay? Radians in second. Okay, and its rated torque of 500 Newton meter. Okay, so what all we have? We have the speed, we have the torque, and we also have the understanding that it's a shunt motor operating at its rated terminal voltage. Its speed is 180 radians per second. Okay, so that's also there. Yeah. Right. Okay. No load speed is 200, and its rated speed is 180 Newton, 180 radians per second. When it's delivering the rated torque of 500 Newton meter. Okay. The motor is used to directly drive a torque. Okay. Directly drive a load. In fact, every motor is supposed to be built such that it can cater to a particular load. And what is this load? It has a load torque TL, which depends on its rotational speed omega R, again in radians per second. So when it's radians per second, please be very careful. Don't use, always remember to use 2 pi N by 60 to convert to radians per second. Okay, such that TL is equal to 2.78 into omega R. Okay. So what do you immediately do? You substitute for TL as equal to 500 Newton meter and divide by 2.78. Okay, so that's all that you got to do, though so much of English is written. Neglecting rotational losses, the steady state speed in radians per second of the motor when it drives this load. So what's the load? It's 500 Newton meter. So 500 Newton meter is equal to 2.78 into omega. Okay, so simply divide by 2.78. You see that it's the same as equal to 179.86 or 180 radians per second. That's enough. Okay. I hope this. Okay. So some of the small differences that have crept in the second installment of DC motors when torque was discussed is very clear to you. We tried to tell you that, first and foremost, we tried to tell you about the stalling torque. Stalling torque is a situation when the speed is 0, which means that all the applied voltage now flows through the armature resistance. If you have inserted some additional resistance, you can control that particular current, as we saw in the earlier session. Okay. Another important aspect that we had better remember happens to be the fact that you have to find out whether what is the relationship between the torque and the current, the flux, and also the speed, if there are any. Okay, so all those things you can utilize. Okay, so another okay, and then if the machine is stalling, it means that it has supposedly a particular speed. Okay, and that particular speed is what you can obtain by changing the voltage, okay, and not and allowing it to run, okay, but using the same voltage ratio. So two voltage ratios can be used to get two speeds, wherein one speed happens to be associated with what may be called as a stalling torque, okay, because of course that speed is equal to 0, okay, and so we saw that as well. And another important aspect we saw was that, yeah, of course, most of the problems are routine, except for the fact that we had three situations emerging in one particular problem where we had EB1, EB2 and EB3, IA1, IA2 and IA3, okay, wherein we saw that the speed reduction gave rise to a reduction in the armature current. Why? Because the torque was proportional, not the speed reduction, the torque reduction, because the torque was proportional to current. Okay, so we use that, okay, and we solve the problem. Okay. Yeah, so that's, and then whenever torque is this is something that I keep repeating. If torque is proportional to speed square, then for a series motor, the current square, because current is flux is proportional to current square will be proportional to N square, or current will be proportional to speed. Okay, so all those aspects can be taken into consideration, and you can also sometimes, at least if one part of the equation is solved properly, as was shown in the earlier problem, wherein you have a numerical value, then you can simply you don't need to go for quadratic solution, because it will take some time. So you just substitute the different values, because you are given some certain values, and see if you arrive at the correct answer. Normally, what I notice is that in such problems, either A or B happens to be the correct answer. So that's all for this time. I hope you've got something or the other from talk discussed in 2 sessions of DC motors. Okay, thank you.